sentences. No, 4 or 5 lines, probably.
Okay, cool.
Yeah. Okay. Okay. So how much? We have 11 to 5 here. Okay, so let's do some example here to make sure that you understand the concept of thermal energy. So I have 100 ml of water at, let's say, 70 degrees Celsius. Okay, and then we have the same amount, let's say at 20 degrees Celsius, B. So which one has more thermal energy? A or B? So which one will have more thermal energy? A and B, and why? Merav?
Is it A? Because the first thing is the individual molecules are moving faster, and then the second thing is there's the same amounts of molecules in either case.
Very good. Okay, so it's obviously it's A, right? So A, because on average, the water molecule has more kinetic energy. It's more kinetic energy, all right? Because higher temperature. Therefore, the microscopic kinetic energy of A is greater than that of B. Okay, since they have the same number, since both have the same number of particles, since both have same number of particles. All right. Okay, and yeah, the thermal energy depends on microscopic kinetic energy, right? All right, so since so it's A, because on average, once again, the kinetic energy possessed by the hotter body here, the higher temperature water, the average kinetic per molecule is higher than over this one. Since they have the same number of molecule, therefore there's more microscopic kinetic energy in this one than there would be in the colder one. And since thermal energy is microscopic potential energy plus microscopic kinetic energy. Since the microscopic kinetic energy is greater, then the thermal energy will be greater. Very good. Okay, example. Another example. So same. So 70 degrees Celsius. One of them L, H2O is A. (50 ml H2O, 70 degrees Celsius. Let's call this C. So which one has more thermal energy? So A or C? David? David? Are you asking me? That, no, no, there's not. And why is that? It's because they have the same temperature. If they have the same temperature, what does that tell us? It tells us that on average, they have the same kinetic energy, right, Max?
It's because thermal energy is inversely proportional to the number of particles.
Yeah. Okay. So, all right. That's good. So, so which one has more thermal energy? Of course, it's A. Whoops, A. Right. Why? Because even though they have the same average kinetic energy per molecule, there are more molecules in A. In A, there's less. Remember, kinetic energy, microscopic kinetic energy is equal to the number times the average kinetic energy per molecule. All right, so remember that, right? That's what it is. Like the average kinetic energy per particle is the total kinetic energy of all the molecule. You add them up, like divided by the number of molecules, right? So here, what happens here is that this one stays the same. This one stays the same because the temperature is the same, right? So this stays the same because temperature is the same. Okay, so there's more thermal energy in A than there is in C, even though like there's, well, first of all, because thermal energy is equal to microscopic potential energy plus microscopic kinetic energy. So also the microscopic potential energy goes up because there are more molecules as well, okay? But yeah, but even then, like the microscopic kinetic energy will be greater, okay? Are you good for that? All right. Okay, so let's do another example here. Now I'm going to sort of, so this is water here. And I'm going to put the number of molecules, okay? So I don't know, like let's say here that Na, how many of, I don't know, let's say it's 2 times 10 to the, I don't know, 30 water molecules, okay? This is going to be oil. Temperature is also 70 degrees. The number of molecules in oil is also the same thing. Why is Benjamin like going out, coming in, going out, coming in? Does he have problem with his internet? Okay. Now, if I ask you, which one has more thermal energy? Can someone answer? Nadav?
Is there any difference between the potential energy between
What,
oil and
what do you
water?
think? Where's this potential energy is coming from? Yes, Max?
It's because potential energy is proportionate to mass, and since we okay.
No, no.
Oh.
Stephen?
I was kind of saying the same thing. I was thinking that like oil's less mass, so like the
No,
potential energy would be.
no, has to do with, no.
Are they have the same?
They're the same? Why?
Yeah.
Yeah. Well, I don't know who's talking. Jason? You didn't
Yeah.
raise your hand, Jason. Okay, why are they the same?
Because the average kinetic energy particle is the same, and also the number of particles is the same.
Okay, repeat this.
The average kinetic energy per particle is the same, and the number of particles is the same.
What does that infer?
The K microscopic is the same.
Very good. Okay, so yeah, very good. So the same number of particles, same temperature, so they all have the same average kinetic energy per particle. They have the same number of particles. Therefore, the microscopic kinetic energy of A and D is the same, right? But does that make the thermal energy the same? Nadav?
Is because thermal energy is also based on the potential microscopic energy?
Yeah, that's what thermal
Did you say
energy is.
that-
Thermal energy is microscopic potential energy plus microscopic kinetic energy.
Can you say that the potential energies would be different because of electrostatic attraction?
Yes. Okay, so which one has more thermal energy? You cannot tell. Yeah, I know. I fooled you. Cannot tell unless you have more information. More information is given. Okay, regarding the microscopic potential energy of each. Yeah, a bit long here. The microscopic potential energy of each. Okay, So the microscopic potential energy depends on the intermolecular forces. The intermolecular forces between water molecule are not the same as the intermolecular forces between oil. So the microscopic potential energy stored in the oil is different than that of water, right? And since you don't know much more, right, you cannot tell. However, they both have the same kinetic. They both have the same microscopic kinetic energy. Okay, because same temperature, as Jason said, and same number of molecules. Number of molecules. All right. Are you good for that? Okay, so once again, thermal energy is microscopic kinetic energy plus microscopic potential energy. Microscopic potential energy depends also on the number of particles. I think dynamite, if you have a little bit of dynamite compared to a lot of dynamite, of course, the bigger dynamite has more microscopic potential energy, more chemical potential energy than the small piece, right? But it also depends on the nature of the chemical forces between molecules. And then thermal energy is also kinetic energy, microscopic kinetic energy, all right? That depends on the temperature, that depends also on the number of particles. Okay, all right, so let's, yeah.
So what information, so what like specifically would we have to be given about this question to make it possible to do?
You would need to be given like the chemical energy content per unit mass.
Okay.
That's what you would need to know.
All right, thank you.
I don't know, you know, like dynamite, I don't know how much it stores. It stores perhaps, I don't know, I have no idea. I'm not a chemist here. Perhaps dynamite stores like, I don't know, 70 kilojoule per gram of dynamite, right? So that would be the chemical potential energy of, well, per mass, right? Yeah, Leo.
Is chemical potential energy related to density?
Well, I don't know. I'm thinking here, like here. Yeah, I don't know. I cannot answer. Sorry. Okay. Okay, so let's go here. Like I'm getting a little late here because I want to get like to the matter here. Okay, so consider okay, consider like heating up a certain substance. Okay, at a constant rate of thermal energy absorption. All right. So here is the I'll put a flame here. Of course, a flame doesn't like really give off like thermal energy at constant rate, but that's not the point here. All right. And let's see here, they have like water. Could be a substance, but let's say it's water here. Okay. So you're heating this up. So thermal energy is being transferred, heat is being transferred into the water. All right, so that's a flame here, right, burner. Okay, so just listen to me here. For the same, so listen, don't write this down here. Don't write it down. Okay, so I'll put it in. All right, so here you have like 2. You have water here, and same amount here. So water, same amount. Let's say you raise this one at a temperature. So this is 20 degrees. Let's say here, this is 20 degrees. Okay, so let's say here you raise this to 70 degrees Celsius. And in B, you raise it to 30 degrees Celsius. Now, if I ask you, which one would have absorbed more thermal energy, A or B? Not like really, really hard here. So what is it? A or B? A or B? Yeah, D.
A.
A, of course, right? Right? It will. And if you do an experiment here, what you're gonna notice here, so this is what you have to write down here, okay? You would notice here that the thermal energy absorbed is equal to the change, how much you change the temperature, okay, of the substance. Okay. I have to go a little fast here. You good? All right, next. So now what we'll do here is we will raise both to the same 20 degrees. So they all start at 20, right? So 70 degrees, right? But this one has more mass than this one. Now, if I ask you, like, which one will have absorbed more thermal energy? So they have the same temperature here. Will it be A or B? Aditya?
It's still A.
Yeah, still A, because it has more
Volume
more.
or mass. Sorry.
Very good. It has more mass, right? So in order to raise like the temperature of a body, a more massive body, it needs to, for the same jump in temperature, you need like more thermal energy being absorbed. Very good. All right. So you have this here. Okay. So you want is good for this? Okay. So here you have a constant proportionality. 2 constant proportionality. You can always sort of, let me sort of put them here now. All right, so let me put them there. You can turn this into an equation, provided you put in front A. What do we have to put in front? What do we have to put in front? A?
A constant of proportionality.
A constant proportionality, and the constant proportionality will be C. Usually it's written as this. Usually it's written more as this. You might have learned this in chemistry. Have you learned this in chemistry?
Next year.
Oh, next year. Where C is called the specific heat capacity. Of substance. All right, specific heat capacity of a substance. It's a physical property. So C is a physical property of a substance. Okay. So each substance have their own physical properties, has their own like specific heat capacity. The unit for C, well, is, whoops, unit, fuck, I don't want to say that. 4C. There you go. So the unit 4C is, you may sort of guess, it's going to be like joule, because this is work. You remember, this is work, thermal energy. So this is in joule. This is in kilogram. This is in Celsius or Kelvin, but we'll put it in Celsius. So it's joule per kilogram times Celsius. Okay, so that's the unit. Example, water, liquid water. Liquid water, the specific capacity of liquid water is this. Liquid water is a substance that has one of the highest specific heat capacity. Now, what does that number here means here? What does that number means here? Well, just listen to me here. So what it means here, it means in order to raise 1 kilogram of liquid water, by 1 degree Celsius, this is Celsius, this is not an E here, you require 4180 joule of thermal energy. Okay, that's what it means. In order to raise 1 kilogram of liquid water at 1 degree Celsius, you have to, the water has to absorb, this 1 kilogram has to absorb 4180 joule of thermal energy. It goes the other way around too. In order to lose, for liquid water to lose, 1 kilogram of water to lose temperature to go colder by 1 degree Celsius, you need to remove 4180 joule of thermal energy from it. All right. Now compare this to, I think, aluminum. Aluminum. Oh, what was it? Aluminum. Let me sort of check. I think it's 190. I'm not so sure. Check in your textbook. In textbook, there's a table for specific capacity. It's on page 270, and aluminum, I got it so wrong. It's 910 joule kilogram per Celsius. So what does it mean here? It means that to raise 1 kilogram of aluminum by 1 degree Celsius, you require only 910 joule, a lot less than liquid water. Okay? Yeah, Max.
Is there a reason why like waters is so much higher than aluminum?
Yeah, it has to do with the hydrogen bonds.
Oh wait, but doesn't aluminum have like metallic bonds which are stronger than the?
Yeah, but that has nothing to do. That's different. That has to do. It's a different mechanism, right? It's different. That might be like. Of course, it's harder to break aluminum than to break liquid, right?
Yeah.
But in order for the vibration here, so what you want is you want aluminum here to vibrate a little bit more. And I guess it requires more energy to get those aluminum atoms to vibrate more than it does for the liquid water, when they can slide past each other very easily.
Okay.
Okay. All right, guys. I'm not going to do an example because it's fairly easy here. All right, it's just like you just have to use like this formula right here. All right, in your textbook, you just have to isolate. You're gonna say, okay, aluminum like needs like, I don't know, 4,000 joule to raise the temperature by 5 degrees Celsius, find the mass, right? So you go on the table. So I'm going to tell you here, there's a little table here, right? So table, it's on page 260 in your textbook, table of, so you look up the specific heat capacity of aluminum, and then you just isolate, right? It's not like really hard. Okay. Key questions. Boomstick from Lou. What is boom? Oh, explosive. Oh, you have to raise your hand, guys. Right? I don't check the group chat. Okay, questions. All right, so I'll see you like on Monday at 9 o'clock. I'll put like some problems for you to do. There might be like quite a few. And if you need some help tomorrow, there'll be a help session at 9:45. So I'm going to be sending this, but don't answer back if you don't want help, right? I don't want everyone to, right? Anyway, I wouldn't be able to go through like 42 people in an hour anyway. All right. Yeah, and then I'll see you on Monday. So any question? Yes, Stephen.
You know when you said that you need to leave like 4 sentences of space?
Yeah, that'll be for next,
Oh.
for Monday. I'm not there yet. Yes, Leo.
So how come for the specific heat capacity, it's written with degrees Celsius? Because everything else we learned in chemistry is always with Kelvin.
Well, like because it's a change in temperature, right? So a change in temperature, a change of 1 Celsius is the same as a change of 1 Kelvin, right? Here it's a change in temperature, right?
Uh-huh.
So that's what matters. So
Okay.
whether the object goes up by 10 degrees Celsius, well, it goes up by 10 Kelvin, right?
Mhm.
So that's why. So it doesn't really matter. So here, this would be like 4180 joule per kilogram per Kelvin too. It's the same unit, same number. Yes, Madame?
Just to clarify, in the formula, it's joules divided by kilograms times Celsius, like all
No.
multiplied together,
Yeah,
right?
it's this. Okay, so let me put it here. All right. That's what it is, right? Joule per kilogram per Celsius. Okay, any questions? Okay, guys, so I wish you like a wonderful weekend. It seems that it's still going to be like nice. Well, I think Sunday there's a bit of rain. It's too bad it's too cold. It should be like almost like 7 degrees higher now. I'm so upset that it's so cold. But anyway, so stay safe and don't forget to remember all those people, all those medical staff, those people who suffer from COVID-19, and also those poor people who got who died at in Nova Scotia. So keep them in your prayer, and remember that the Lord has conquered death. Never forget this. All right. Okay, guys. So I'll stay just perhaps like 2 more minutes if some people wants to talk to me or something, like if you haven't copied everything here, especially Benjamin here. Otherwise, I'll see you on Monday. Okay. Bye-bye.
Bye.
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 Bye,
Bye.
sir. Thank you.
Bye.
You're welcome. Very welcome. Bye-bye.
Wait, sir, can I just ask you a really quick question?
Yeah, you can ask a quick question. Hopefully it's a
Okay.
quick answer.
What exactly is chemical energy again?
Well, it's potential energy. Okay. So all right, let me sort of put this here. All right. Where's my spring? Oh, my spring is. Had a spring. Oh, well, I'll use this. When I stretch this, I'm storing elastic potential energy, right?
Mm-hmm.
Okay. It can do work if I release it, right?
Yeah.
Right. Now, or let's say here I have a spring. and I compress the spring. I have a toy, right? And the toy here compresses the spring. It stores spring potential energy. Okay.
Mhm.
And I can release this spring potential energy. It can sort of make work for me. It can sort of start like turning wheels and the toy, and then the toy will get going. All right. Okay. So chemical bonds, in the same way as I can store potential energy in the spring, chemical bonds store chemical energy. All right. And you can release this chemical energy in the same way here that if you have something compressed, right, there's a little thing that keep it compressed. You can sort of flip this off, right, and release the spring. You release the potential energy stores. Same thing with the chemical bonds, right? So chemical reaction, what you do is you release the chemical energy that is stored in some bonds. So example, like nitrogen bonds are very, very strong. They pack a lot of energy. And if you can sort of make them release this energy, such as in dynamite, then you're going to have a lot of thermal energy being released.
Okay, so for example, right, like, because I remember like you like a few days back, like using an example of like eating. So when you eat, you store chemical energy, right?
When you eat,
Yeah.
heat,
Or
you
or
eat-
so when you like consume the food.
oh yeah, yeah. But that's exactly what happens here is that like your food molecule here has chemical energy in the bonds. And what you do, what your body does is that it breaks it apart, and then release energy in the form of heat. You're a hot body organism. You need heat to survive.
Okay.
So this heat comes by breaking like the food molecules. Of course, you need also you need energy not only to keep your body high temperature. You need to move, right? So what they do here is that those food molecules here are broken down and they're kind of rearranged in other molecules that stores all this chemical potential energy for later release. So if you this is called like ATP. ATP is the energy molecule in your body,
Mhm.
and ATP here like stores chemical energy for release. So when you do an activity, ATP is being broken down, releases energy, and then make you move, like move your muscle and so on.
Okay. All right. Thank you, sir.
Yeah. All right. Oh, David, why did you come in late? I don't know. How far do you want me to go? Ooh, la, 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 la. This? It's a little. I started there. It's going to go back here, but Forrest, do you have a questions?
Sorry,
No?
I
Yes?
just haven't left yet.
No, it's okay. Okay. Come on, David. You have to get up. You have to follow a schedule, David. If you don't follow a schedule, then wasting time. Oh, you didn't sleep good. Yeah, it has more. Yeah, and it has more kinetic energy because if they have the same temperature, on average, they have the same kinetic energy. But since one body has more particle, when you add this up, it adds up more than the other one, right? So there's more thermal energy, more microscopic kinetic energy in an object that has more mass than an object that has less mass for the same temperature. And there's also more microscopic potential energy also because there's more particles as well. It's TH for thermal. TH? Yeah, thermal energy. In your book, they call this EH. H stands for heat. It's the same. Well, no, the heat is transfer of thermal energy. Yeah, it's a EH or yeah, thermal. It means thermal energy. But heat, EH and ETH is thermal energy. But H stands for heat. Well, heat is a transfer of thermal energy. It's not thermal energy, it's a transfer. How much is transferred? Some way, in the same way as work, right? Work is a transfer of energy. So heat is a process. It's not a state. What's that? Energy is a state variable. So at a given point in time, there is a certain amount, a definite amount of thermal energy, a definite amount of mechanical energy, right? Okay, and heat is a process by which like a material goes from one state to another state to process. I don't know the historical reason. I never asked myself why. I just use it. I don't know. Maybe you can find it. Why are they using Q? Well, it's not French. I don't think in German. Let me see here. German. That's correct. That's correct. Heat in German. You see heat in German. Boy, Hitze. No. No, I don't know why, where it comes from. So, whoops. Oh. It's something that on Monday you're gonna fill in. I didn't have time to cover this. So. Okay. I know, but listen, I need because what are you gonna do next year? You haven't learned the basic, right? So, I mean, I wouldn't know like what to do next year, to tell you the truth, right? So I want you to sort of be prepared. Right? Okay. Bye bye. Have a good day.